has to be equal to g of b plus 4 pi, which also has to equal g of b plus
2可以看。
So our result here, right, is that m has to be an integer. So this is just establishing a boundary condition. So m has to equal a positive integer, a negative integer, or a 0. In the interest of actually being able to start the hydrogen atom, we could do the same thing and come back to this side of the equation, setting it equal to minus m squared. And now we have something that's written in terms of m and l, right? And so what we get is that f of L and m of theta is equal to, and this is where you're probably not super thrilled. So this is true where L is equal to 0, 1, 2, 3, and then M is going to go 0, plus or minus 1, plus or minus 2, all the way up to L, plus or minus L.
Cosine theta square minus 1, right?
What's that?
Cosine theta square minus 1.
Yeah, I'm sorry.
Okay.
What's the exclamation point again?
Factorial. So if it's L factorial and L is 2, it's 1 times 2. If it's 3 factorial, that's 1 times 2 times 3 is 6. Yay? If So if L equals 0, then M equals 0, right? Because L goes from 0 to whatever it wants in integer steps. M goes 0, plus or minus 1, plus or minus 2, all the way up to plus or minus L. So if L is 0, M can go from 0 all the way up to 0. So in that case, I'm going to describe YLM of theta in B as equaling FLM of theta times GM of B. And so I'll tell you that L equals 0, M equals 0, Y 0, 0, LM 0, 0 is just equal to 1 over 4 pi under the radical. That's friendly, right?
YOO, what does YOO mean?
You?
L equals 0, M equals 0, so Y, L, M.
Okay.
So this doesn't look so bad, right? If we say that psi is equal to R times F times G, well, F times G, that's not bad, right? Well, let's look at L equals 1. What values can M take on if L is 1?
Equals 1.
0, 1.
And minus 1.
And minus.
Oh, Julio, good job.
So M equals 1, M equals 0, M equals minus 1. I'm just going to do them in rank order. So that's equal to minus square root of 3 over 8 pi times sine theta e to the I b. Okay, that's a little less friendly, but these are called the spherical harmonics, by the way. You can find these in tables. So y1 minus 1. Still not, I mean, so terrible, right? And now, let's try L equals 2. If L is 2, what values can M take on?
2.
2, 1, 0, negative 1, and negative 2?
Correct. This is clearly going to be the last set of spherical harmonics we do. So y22 is 15 over 32 pi under the radical sine squared theta times e to the 2I phi. y21 minus 15 over 8 pi times sine theta times e to the I phi. The 0 case, and I may actually stop with this one, because I'm running out of space. y20 is 5 over 16 pi times 3 cosine squared theta minus 1. And then, I don't know, I think I'm going to you can determine them from our G and our FLM. But I don't really have much more space, so. Let me do the minus 1 case just because, well, it's not easy, but it looks slightly distinct. So y2 minus 1 is 15 over 8 pi. The ones that end in 0 tend to be the sine theta cos theta times e to the minus I phi. Hooray-ish.
No.
Okay. So, G, so this is really just taking f times G, where G is this. And so, where your m values are, that's going to adjust what the power of e to the I you're getting, right? Note when m is 0, e to the I 0 times phi is just 1, right? So all the ones that have 0, the e to the i's don't show up. For this, it's sine raised to the absolute of m divided by 2 raised to the lth power times L factorial. And then we're going to differentiate cosine squared theta minus 1 to the lth power, but we're going to differentiate it with respect to cosine theta, L plus absolute m times. It's a good way to spend a Saturday afternoon. Or, since these are so important, tables of spherical harmonics have been up and available for, I don't know, more than a century.
So would y2 negative 2 be square root of 15 over 32 pi sine squared theta cos squared theta?
Sine squared theta e to the minus 2I phi.
Yeah.
Is the physics solved for this number or mathematician solved for this number?
Let's make the mathematicians do it.
Oh no, I should change my
I got places to be.
Got research to do.
So, no, these have been done for a long time, right? It's not. Okay, so let's jump forwards.
I think this is physics class.
So we could also, now that we've done this, come all the way back here to our equation for R. We can create an effective potential written in terms of V and in terms of some constant, and we can solve for R equation just like we solved for G and we solved for F. Instead, let's not. And I'm going to give you that when you do that, note that we got a pair of quantum numbers, L and M, from these two. We're going to get another quantum number, N, from solving this R equation. And so N we are going to name the principal quantum number. Its allowed values are just positive integers. So the number of allowed states are infinite. Any, instead of saying that, let's just say any integer. We also got L from this. We're going to call this the orbital quantum number. and its values are allowed to go from 0 all the way up to n minus 1. And so this allows for n possible states. And then we had m or ml if you prefer. I really don't care which one you use. And you could call this orbital magnetic, you could call this magnetic. And this one is allowed to go from minus L all the way up to L in integer steps. And so this is allowed to have 2L plus 1 steps.
You do MS.
What's that?
MS.
So this is the point that I was making. If you solve the Schrodinger equation in 3 dimensions, the things that pop out of it, you get 3 quantum numbers. When you actually try and build the periodic table, you find that those 3 quantum numbers don't return the periodic table. And so what you need instead is yet one more quantum number. And that one more quantum number is associated with spin. And so these are the quantum numbers that you get from the Schrodinger equation. Empirically, we are going to add yet one more. But I'm not going to add that just yet. I will in a minute.
All right.
So, I also will give you that. Now we get to go all the way back to the beginning, plug this in, and solve for the quantized energy, except that I don't think we want to do that. So the quantized energies are such, I guess I need to put a Z here also.
Is that E
But if it's-
square?
what's that?
Is that E square?
Yeah, charge of the electron. So 1.602 times 10 to the minus 19 coulomb. If we're talking about hydrogen, Z equals 1. Helium, Z equals 2. Lithium, Z equals 3, so on and so forth. But hydrogen, Z equals 1, and then it really is just minus 13.6 electron volts over n squared.
Mr. Wang, you say EV means electron volts?
Yes, ma'am. Unit of energy. Small unit of energy. So 1 EV is equal to 1.602 times 10 to the minus 19 joules.
Oh, okay. Thank you.
662.
1.602 times 10 to the minus 19 joules. So let's do this in 2 steps. I'm going to move this to the other side. Okay, so Okay, so to simplify our lives when we're talking about chemistry, rather than continuing to talk about L, N, L, and M, we'll oftentimes refer to the N equals 1 shell as capital K. The N equals 2 shell is capital L, so on and so forth. Subshells are the L numbers. So L equals 0 is S, L equals 1 is lowercase p, L equals 2 is lowercase d, L equals 3, lowercase f, so on and so forth. Hooray-ish. Then let's look at sorry. It's not terrible. Okay, so now let's build ourselves a little bit of a mapping. Four. And then don't care about this one so much because I'm just putting it there for funsies. And then we've got okay, so let's look at allowed electron transitions. And oh, good golly, I'm going to come to regret this. I go really go all the way up to that one. Why, Mark? Why? Okay, so there's one set. We can also do this set, this set. We can go from here to here, here. Any of these three to any of those ones. I can go So if you start to look at allowed transitions, this isn't a full set because I think that this is crazy enough as it is. One of the things that you're seeing is that you can only move over by one, right, along L. And so our,
That's the transition state of the orbitals the electron can take, right?
yep, okay. So
Where, like it looks familiar.
What's that? Is this for the electron moving?
So that's what the electron is allowed to do. Give me 1 second to figure out where I am in my notes.
Is it associated with ionization?
So,
Okay. Yeah.
so selection rules for transitions. M is allowed to either not change or change by exactly 1. L must change by 1 in any transition. So let's see if we can make some headway with this. I guess I can take that half. So psi of NLM, we've already said that it goes as R times F times G. Our equation for R is a little ugly, so I'm skipping that one. But let me write up psi 100. So this is the n equals 1, L equals 0, M equals 0 case, right? We had that, oh, it's on a hidden board. Is it?
Let me just behind.
Probably on this one, right? Yeah. So n can take on any integer, L can go from 0 up to n minus 1, M can go from minus L to plus L. And so if n is 1, L is pinned to be 0, right? Because it can go up to 0 to n minus 1. 1 minus 1 is already 0. And M is bound from minus L to plus L, integer steps. So if n is 1, L and M are going to be 0 for us. So psi 100 is equal to C 100. And I'll give you the constant in a second. So this one, I really feel like I have this somewhere. There we go. Oh, that's 2. Well, along Z, this looks somewhat spherical, right? You can see that if this is psi, what is psi squared again?
Probability.
Density.
Probability of finding the thing, right? And so if I take some constant times e to the minus z r over a naught, and I square that, it's just twice this, right? And that squared. Yeah?
What's A naught?
A naught is the Bohr radius,
Oh,
and
okay.
we'll come to that. It's just a constant value. So about half an angstrom. So note that psi squared is just e to the minus 2 this, right? And so when r is small, that's when it is kind of at its biggest, and it kind of falls off, but it falls off radially, right? And so you get something that kind of resembles this with a lot of spherical symmetry. And so it has no angular momentum. Remember, how did Bohr make the Bohr atom work? So Bohr did it by quantizing the angular momentum of the electron. That was how he came up with the allowed energy levels. But if you follow this through by quantum mechanics, the ground state has no angular momentum. And so that's kind of a problem for us, for the Bohr atom at least. We've seen consequences of that in our lab, where I told you that you couldn't have certain transitions because it would violate conservation of angular momentum. Probably on Monday I'm going to have to briefly show you that. But if we say that the electron is somewhere, that's basically this normalization criterion that psi star psi dv has to equal 1. dv in spherical coordinates, r sine theta dphi times r d theta times dr is r squared sine theta dr d theta dphi. And so let's try this just really quickly. So zero to infinity, 0 to pi, 0 to 2 pi of psi squared times r squared sine squared, sine theta dr d theta dphi. And we can write this 0 to 2 pi dphi times 0 to pi of sine theta d theta times 0 to infinity of C100 squared e to the minus 2 zr over a naught dr. And the nice thing about this is you can see when we have fully separable solutions, like if we assume that R, F, and G are independent of each other,
The convolution, say.
then I can separate out the integral, right,
Okay.
into pieces. and then multiply them together. If we do that, well, what is integral? I'll do this first one for you. Integral of d phi from 0 to 2 pi is just 2 pi. No, that was the one I called. If we actually try this, we get, let's see, 0 to infinity e to the minus 2z r over a naught. Oh, I dropped an r squared, didn't I?
On C.
This was psi squared r squared dr. That r squared had to come in there.
And then on the original one, the C didn't have the square. The Y one. I mean, C, phi. I can't say it. Psi.
Where did I miss this? Sorry.
No, I was asking, you put the square on the C in the original, that one. But it's cut, yeah. I understand.
We're okay? Okay. I'll just tell you, because I'm basically out of time. This is a naught cubed over 4z cubed. And so that gives us that this is equal to 4 pi times c100 squared times a0 cubed over 4z cubed, and that has to equal 1 by normalization. From that we can solve that c100 is 1 over root pi times z over a naught to the 3/2, finally yielding that psi 100 ground state is just 1 over root pi z over a naught to the 3/2 e to the minus z r over a naught. That is the ground state of our atom. If we let ourselves refer to our periodic table, you can see z equals 1, and so this for hydrogen is psi 100 is 1 over root pi times 1 over a naught to the 3/2 times e to the minus r over a naught. I'm out of time.